All right, so again, test 10, 17.3, all of chapter 19, and then 20-1. Okay, all of chapter 19. Now, in 17.3, we talked about electric fields. And to start, I'm going to put the formula up because I think it's very useful to see this, to understand what we're talking about. The first thing I recognize here, okay, is that the formula for electric field is really only based on two parameters. What is Kc? Why does Kc not really matter too much in the sake of a problem? It's a constant. So Kc does not change. So that remains the same way. But if there's more charge, Q, it means you have a stronger field, E. How come? They're directly related. E equals KCQ over R squared. Well, right away you recognize this is in the numerator, this is in the numerator. Bless you. These are directly related to one another. These are indirectly related to one another here. So if I move further from the source, the field gets weaker. And we've spoken about this idea. The same thing works with gravity, right? If two objects move further apart, the distances between their centers increases, and it gets weaker and weaker of a force. Now, electric fields are not forces. Again, they're not forces. You could know that. You could look at the units to determine that. Units of electric fields are newtons per coulomb. If it was just newtons, then it would be a force. The electric force is what we talked about in section 17.2. This is the electric field, and we use the term field strength or field intensity to describe the actual value of the field felt. Now, with that said, let's take a look at what these fields physically look like. Say we've got a positive source here.
Did you have green quizzes?
I did, actually. Thank you for reminding me. I meant to get them back to you today. I know, I want you to get them back, actually. So, draw the lines around this positive source. And then to the right of it, draw a negative source.
Oh my god, I hate this one. War found me scary when I did
For all of you never stop talking, Shimon, I appreciate you reminding me of this. You know?
The insults are just flying. Are we in Congress? Live tip. I haven't seen this much in Congress.
Just have my if I was in Congress, my filibuster would be, I'd read the biography. I'd read the biography about Zodiac Killer, like every time there's a Zodiac Killer, I just replace it with Texas.
Just deny anything they say. No,
oh yeah, I changed my name now.
What's your name?
Gab?
Never forget.
Still pronounced the same way.
I give you the quiz back, right?
Don't pronounce it any differently, Samantha.
Wow, I got it.
Never forget Morgan.
What should the field lines look like around that positive source right there? Yes. Why are they extending away from the center?
Oh.
I did that.
Because why?
I forgot the stupid loop-de-loop.
Next up. The arrows always indicate, as Christina just said, the direction of positive flow. So if I had a proton somewhere that was randomly put in space around this area, that proton would want to move away from the positive source. Since the proton would want to move away, it would have to be drawn like this. So field lines are drawn outward from a positive source. For a negative source, it is inward. Now, there are several things we should recognize about a source. First, again, the stronger Q is, the source itself, the stronger the field. The further away you are, the weaker the field. If I triple the distance from the source, what does the field go down by a factor of? Sophia? 9. Where are you getting 9 from?
Because it's cube.
Not cube. The other one?
Squared.
Squared. There it is. Okay? This distance from the source its variable is squared in the formula. So as a result, if I double the distance, the field goes down by a factor of 4. If I quadruple the distance, the field goes down by a factor of 16. And I keep talking about the field, I mean the field strength or the field intensity. Okay, yes?
So if it said, say if the quiz question was like draw a field present or a negative source, it would have things coming in because positive wants to go towards negative.
Remember, the test charge is always a positive charge, and that's what we're looking at. Remember the quick lab you guys did? The hockey puck one? When you dropped the positive source on the page and there was the puck nearby, it showed the puck moving away. It had a vector arrow showing the force it would feel away from that source. That's indicating exactly what you're seeing here. Except when you did it with that lab, it showed a lot more arrows and a lot more in depth of a field that you could see. This is just a sketch of that. There were several characteristics about field lines that we talked about. There were several characteristics. Give me one of them about the field lines. There's something about them that we could say. We had like 3 or 4 characteristics.
The strength depends on its magnitude.
Those are the same words, though, strength and magnitude. It's like saying your weight on
No,
a...
I hear it's
You're on the right track, Ann, but it's something else.
The magnitude of the field lines is proportional to the number of lines.
Yeah, the more lines you have, the stronger the field. Now, again, this is completely arbitrary. I can't tell by looking at this diagram that like the field strength is 20 newtons per coulomb. That's not because the lines are showing that. But if I had 2 sources next to each other that looked identical, right? But one of them had more field lines than the other, you could automatically assume that the one on the right was a stronger field. Okay, but it's not telling you about the actual value of the field itself. Is that clear what I'm saying? Okay, the lines doesn't actually tell you the amount. It tells you relatively, this one would be stronger than this one because there's more lines. Okay, yeah. It's not a numerical quantity you're getting from the number of lines. It has nothing to do with that. It's just a relative value, which is greater. Field lines don't cross. So when you draw field lines away from a source, even if they're going toward another source, these sources would never cross in field lines. They'd both be bending upward because they're repelling each other because they're both positive. What else? I'm trying to think of other stuff for electric fields. For your example problem that you might want to look at, if you remember, we looked at one in class, that the example was the following. There was a positive source here and a negative source here. And we wanted to calculate the field felt at some location in between them.
You would have the distance.
Now, in the class, it was half the distance. That location could be anywhere. Okay, it could be anywhere. It could be out here. Take a look at where I just moved it to. It could be out there. Well, if the location was out here, if I think about a positive test charge always, which way would this want to move as a result of this? To the left. Give me a direction. Left, right? Left, correct. Now, due to the negative source, which way would this move?
Right.
To the right. So again, this positive source would push the proton away. This negative source, though, would pull it toward. So this is very similar to your free body diagrams you drew in section 17.2, where you had to draw which way was the particle being pulled, left or right, and you had to sum them. So if I'm getting pulled to the right by this, but I'm getting pushed to the left, assign signs to them. So when you calculate the field because of this, because it's pushing it left, give it a negative sign. That's fine. If you calculate the field as a result of this, because it's pulling to the right, give it a positive sign. And then you could add the negative number you have from this one to the positive from this one and see in the end which way would it actually move, positive or negative, depending on which was stronger.
Yes.
I had a feeling that was good. Now, if the 2 sources were both positive suddenly, which way would this proton or test charge definitely move? To the left. It's got to. That could be a multiple choice very easily. I'm not going to ask you to calculate it, but if you had a test charge right here, it would want to move to the left. What if the test charge was here?
It
It might stay the same if these are absolutely identical and it's perfect symmetry. But if there was any perturbation, up or down, even a little bit, it would move in that direction, either up or down. Okay? I mean, that's really the idea. This X can be anywhere is what I'm getting at, okay? This location can be anywhere. I gave a good example mathematically with the other class. Watch that video. Look at the example in your notes mathematically. Look at question 38 from the problem set mathematically. If you can do those three, you should be set for this mathematically on the test, this portion. The second section, 19-1. What was 19-1 all about? Circuits was 20-1. Current. The current, which obviously leads to circuits, and we're going to talk about that obviously. But 19-1 was about current. No, that was 19-2. Now, we can see that there is a similarity, or there's a relationship between these two things. In current, we know that the current is the amount of what? How do you think of the current? As the what? Yeah, rate of movement of charge. Very good. Okay, and the current mathematically is defined as this. Change in charge in a given time. As Chris just said, in a given time, that means rate. And Chris said, the rate at which the charge is moving. Charge is Q, T gives you rate. This is the rate at which the charge is flowing. Okay, the current is the rate at which the charge is flowing. Now, if I were to relate this to circuits, because now that you know circuits, I can make a quick statement about it. Here's your circuit right here, right? Well, if I want to calculate the current, I could pick a point anywhere in the circuit. So pick a spot. I'm going to pick right here where that yellow line is. If I could calculate how much charge crosses that location in 1 second, that is the current. Again, current is delta Q. Delta Q is charge. Change in charge. The amount of charge that is passed. The charge that passes that yellow line every second, the amount of charge, is defined as the current. The units for current are A for amps. Okay, but really, it's coulomb per second, which is, again, amps. A coulomb per second is an amp. Coulombs are units for charge, the amount of charge that is passed that location. T units are seconds, coulombs per second.
So is it equivalent to when you found the slope of a line, it'd be the same like finding this one section because you can apply it to the entire thing? Like you can apply a slope to an entire line.
Well, this is like the slope actually. This is just like slope. Remember, slope is defined as rate of change. This is the rate of change of your charge. So if I were to do this, Siobhan, if I had axes and I called this Q and I called this T and had a line like this, the slope of that line would be the current. Because look, change in Q over change in time. Wouldn't that be how you calculate slope? Delta Y over delta X? The slope of this is delta Q over delta T. That's it right here. So the slope of this line given would be the current. Absolutely. Okay, it would be the current. When we were talking about current, we had a lot of other things we alluded to. So we talked about drift velocity for a little while. What was drift velocity? What was that whole idea of drift velocity? What was the whole idea of drift velocity? What was the whole idea of drift velocity? It's a little bit confusing. It's not something easy at all. Anybody knows? I see your hand, I know. I just want to give others a chance to respond. You understand what it is? Besides reading out the definition? Yeah.
It's like,
In a circuit, you have charge carriers that are moving, right? They're moving along. And they bump into those metallic atoms along the way, those copper atoms. And as they're moving along, there's an electric field that's pushing them along. That's really what's happening. You turn the light on. As soon as I turn the light switch on, these lights is a little delay because the type of light bulbs. But as soon as I turn the light on, it closes the circuit, which establishes some terminal voltage on the actual circuit, which means that there's a field. That field pushes the charge carriers through the circuit. The field itself is established instantly because the field travels at the speed of light. But the charge carriers travel a lot slower, physically slower. They move a little bit at a time. And this is where I showed you those simulations, with those FET simulations I was showing you, with the charge carriers slowly moving while the electric field is flying through. Okay? So drift velocity is the velocity of the charge carriers, which is much, much, much less than the actual speed of light. Because those charge carriers are just moving along slowly. As they get to the appliance, their energy is used up. They go back to the battery where it's then recharged. You should know that diagram. You should understand, ready? That as the charge carriers move out of the positive terminal, remember, we look at the direction of positive flow, even though it's really electrons, right? We look at the direction of positive flow. Positive flow would want to leave the positive terminal and go like this. So these are the charge carriers. They've got a lot of energy right here. They leave the battery. They get to the appliance. What does the appliance do to the energy? It uses it. It dissipates. It bears the load. Remember that term? We said it's a load-bearing element. This resistor takes on the energy from the charge carrier. It uses it. And now the charge carrier's got no energy left. But the other charge carriers behind it are pushing it along. They're saying, come on, get back to the battery. Get back to the battery. You can get more energy. It gets back to the battery. It gets recharged. The charge carrier then goes through the cycle again and again and again. Okay, this continues to happen over and over.
You said the resistor is the appliance?
Yeah, so like any appliance, any element in your circuit is a resistor. Even a wire technically has a little bit of internal resistance to it. Okay, a little bit of internal resistance. In addition to this with current, we talked about alternating versus direct currents. I gave you a quick simulation of this using, again, that FET simulation that really showed you how to do this. But direct current, to demonstrate, does this. Ready? The particle or the charge carrier goes in one direction only the whole time. But with alternating current, these terminals keep switching. So this charge carrier leaves here at first, but then imagine these two switch, and now there's a negative terminal here. Well, then it's going to get pulled back. It passes through, it gets pulled back. It passes through, it gets pulled back. And the alternating current has to do with charge carriers that keep moving over the battery back and forth. Alternating current is the most prominent one that we see today. You don't see direct current much unless you're somewhere where there's not a lot of infrastructure for electrical grid work. So in a lot of countries around the world, you see AC current. You see DC current in some countries that don't have some sort of infrastructure for an electrical grid in their country.
What do trains use?
What do trains use? I'm going to guess alternating current. It's got to be AC. I mean, you're talking about regular trains like subway trains, right?
Or you mentioned subway or mentioned.
Yeah, it's going to be alternating current. That's what they receive. Alternating current is a lot safer than direct current, by the way.
How would that be asked? Like a question between, like, what's the difference between direct current and alternating current?
Sure. I mean, you should just know about what they are. I mean, I talked about it in class, how alternating current, remember how when there was alternating current with that generator, what happened? The light was flickering the whole time, wasn't it? But we don't see lights flickering. Again, why is that? Flickers faster than we can pick it up with the eye, right?
Even though it's always happening.
You just don't see it. You will not see these lights flickering, even though they are flickering, really. Flicker at such a high frequency that we don't actually recognize it. Another thing we talked about in this section was the difference between a generator and a battery. Who can explain? A generator versus a battery. What is the difference between the two? Between the two of them. Nick, go ahead.
A generator creates energy and a battery stores energy.
On the right track, good. More than that. There's more to it than just that. Sam?
Doesn't a generator switch chemical energy into electrical energy?
You're on the right track, but the other one. That's the battery. The battery takes chemical, converts it to electrical. And what about the actual generator?
Generator is mechanical to electrical.
Mechanical to electrical. Mechanical. So remember, a generator is like turning a little hand crank over and over to power some sort of a light bulb. A battery is literally taking a battery, taking the chemicals inside of the battery, converting that to electrical energy. Now, you can charge a battery with a generator though. Again, you can recharge the chemicals in a battery with a generator and then use that battery to power some electrical appliance. So you can indirectly use a generator through a battery then to the appliance. A car works just that way. Again, the car battery runs. If the battery is depleting, you turn the car on right away before the battery dies out. Once you can get the car on, the actual car acts as a generator, charging the battery, recharging it. Carolyn.
How does the, like, I don't know, it's me and someone else that had like a generator that you don't have to crank, like how does that work?
So those aren't really generators. What they are, well, I mean, they are generators, but here's what happens. The ones that you go home, you don't have to actually pull like a strand to start. There's an electrical battery, there's a battery of some sort that starts it up. Once that battery starts it up, it uses gas. It's usually gas powered or some other sort. Yeah. I mean, you could have a generator that's actually.
So it's just like an engine.
The term generator is widely used at home use, when in reality it would not be a generator then, right? It would really just be a battery powering your house. But if there's something that's turning, some sort of a turbine that creates electrical energy, that's what a generator really is. It generates energy because of mechanical input. A dam actually turns these turbines, which creates electrical energy. It's a generator. So if you have the one at home where it's literally like the new Tesla battery, you know the new Tesla battery?
Yeah.
I mentioned this before, I think. There are these like huge at-home batteries that are supposed to last a really long time. And the good part about it is that you don't need an electrical system to use it. You could have just this one thing in your house, and you draw all your energy from that. You could recharge it. You could do a lot with it. The model worked out well, but they actually just they stopped making the bigger version. They were finding that the bigger version of the Tesla battery wasn't selling well, so they're only selling the smaller version of it now. But it's extremely prominent right now in countries that don't have an electrical infrastructure. If you don't have electric lines coming to your house, how do you get electricity? You can't, unless you have a generator. So people are buying these Tesla batteries, and they're actually using them in other countries, and a lot of people that are philanthropists and stuff are donating these things. I think I talked about, what's his face? Who's the rapper I talked about that's doing all the work in Brazil and Africa?
Akon.
Akon is doing a ton of work right now in a lot of countries. And the work he's doing is extremely important because he's developing infrastructure. It's not about like solving the problem with money. He's saying, you know what? That's not going to work. You can give these countries or other countries that don't have a lot of resources all the money in the world. But if they don't have the actual infrastructure for it, it's not going to be used. Now, giving money to some countries might not go to the right source. Maybe you give money to go somewhere and somebody else gets it somehow. There's corruption. Even in the U.S., we know that clearly there's corruption, right? So instead, he's working on this thing where he's building these infrastructure in these countries so that they can have electricity delivered to their houses, so that they can have streetlights, so they can walk safely at night, so that countries that usually only get up in the morning and go to bed at night when the lights go out because there's no electricity can work into the night and do more work. I mean, you don't take for granted ever, but if you think about it, imagine not having electricity at all. Just imagine that. Think about it for a second.
The entire world.
What would you do after 6 p.m. every night?
Sleep. Read a book.
Read a book. That's what you used to do. You'd have a candle lit. You couldn't use your cell phones because you couldn't charge it. So think about this, guys. It's actually insane how much you use electricity every day, everywhere. No matter what you do, you use electricity. There's a show that was out for like, I don't know, 2 seasons. There was a show that was out for 2 seasons. Anyone see it?
What's it called?
It was about, imagine electricity just stopped working one day.
Yeah.
Revolution?
No, the colony
Nobody's seen
on
What's it
Discovery.
called? No, not Discovery.
Revolution?
Revolution. Yeah.
I used to watch it.
I watched it for a little while. It was meh, you know?
There was a show on
Yeah.
there was a show on Discovery called Colony where it was post-apocalypse and they had to survive like in this warehouse.
And they kept getting attacked by all these people.
Interesting.
So
Well, Revolution was probably very similar to that, because Revolution, the concept is that there's like an airborne virus that somebody puts out that stops electricity from functioning. No, it would never happen. It's not possible. But it would stop all electricity from ever functioning. So they went back into like, it was like swords and stuff suddenly. And like, it was
And
crazy.
muskets.
Because suddenly you couldn't use like a milling thing. You couldn't make guns anymore. You couldn't even manufacture bullets because there was no electricity to actually use the machines to make the bullets. So suddenly everybody was like preserving ammunition, they had swords and stuff. It just changed things up a lot. It'd be a crazy world though.
And then they
Anyway.
call that an attack helicopter.
And then they canceled it.
That was the part where they realized they could turn electricity back on in certain areas by debugging the virus or something.
The crazy
Or some computer code. Yeah, it was really
the
stupid.
crazy scene from that first was the first episode when all the electricity goes away and planes start flying out of the sky? That first of all, they would not have to glide down.
Yeah, I mean, they would
They
still
were
be
like
able to.
twirling down.
Yeah, the idea was that like once you lose electricity, your jet engines can't run anymore. Nothing's gonna turn. The turbines stop turning.
Yeah, but it's not like
It just went like this. Yeah, I know. Whatever. Resistance. Resistance is what? The opposite of? Okay? Resistance is what? Star Trek, yes. Resistance, nice. The current wants to flow. But if the current is flowing and there's like a rock in the way, I mean water current, it moves around it. It takes the path of least resistance. So in a circuit, like lightning, yeah, the example you gave in class, very good, lightning. So in a circuit, the current wants to flow through the circuit, but the resistors or the appliances are stopping it from flowing at the rate it wants to flow at. With resistance, we talked about 4 parameters that affect the resistance. 4.
Oh,
Give me one.
the length of how.
Length of the wire is 1. Give me 2. Another. Temperature of the wire. Give me another.
The cross-section.
Cross-sectional area. And the last one? Last one? And? Material. Material, it's kind of arbitrary. We don't know. Based on the material, you have to know about the material itself. But temperature, we know, is directly related. Think about your computer. As the temperature goes up, the computer starts to slow down. More resistance. Think about it. It's not really physically correct to think that way, but it is a good analogy. Length of the wire. Longer the wire, more resistance, because there's more collisions between the charge carriers and the metal atoms. The bigger the cross-section, the less resistance. That's the only one that's indirect, yeah. And think about a pipe. If you have a bigger pipe, right, the flow can flow a lot easier, a lot faster. If the pipe gets real small, right, it's going to slow down the particles. Now, with water and fluids, it's a little bit different because you're talking about pressure head and volumetric flow rate. We'll get to that later in the year. But with electrons, it's obvious. You get a smaller wire, less electrons or charge carriers go through, thus less current. Okay, smaller cross-section, less current. So the current and the cross-section are directly related, but the resistance and the cross-section are indirectly related. Okay, current and resistance together, though, are indirectly related to each other because of this formula right here. If the voltage is held constant, which it is, the voltage you get from this outlet is 120 volts. It's not changing. If the voltage is held constant and suddenly the resistance skyrockets, what's going to happen to the current? It's going to drop. Okay? It's going to drop. When do you have a short circuit? When do you have a short circuit? When there is? When there is?
When the charge doesn't go through the resistance.
Yes. When there is nothing to resist the flow. If the electrons or charge carriers keep flowing through the circuit and the energy is not used, it's going to get hotter and hotter and hotter. The battery's going to heat up. The wire's going to heat up. Yesterday, some of you actually noticed this. Some of your wires, or the other day with that little foil, were actually getting hot. And if you actually just attach the wire to 2 ends of a battery and let it sit there, the wire would heat up. It actually physically would heat up. Now, you're drawing 3 volts out of those little batteries. Even I was showing in the other class, a drill gun that I use in the engineering class, it's only 18 volts. This is 120 volts coming out. A lot more than what you're getting from a battery. That's why you can take a 9-volt battery and touch it to your tongue. And you get that like tingly feeling. It's you're connecting the circuit. The flow goes through your tongue. It's only 9 volts though, so it's not going to hurt you. 120 volts through your body will hurt you. Not kill you, but hurt you. Exactly. Or if you're like me when you're a kid, I told you guys. I was walking by an outlet on a wall, which I didn't realize there were wires, and my uncle never turned electricity off, and I went to like shut the switch off, and I was thrown back a couple feet. But you don't, that's not going to kill you, but you will get shocked. You'll get like tossed. I want to keep going because time's going to run out. Ohmic versus non-ohmic variable resistors we talked about. A variable resistor is the potentiometer. That was like a dimmer on a light switch. Remember the light switch you can dim on and off. It changes the resistance in the circuit, which changes the amount of intensity of the bulb itself, of the light coming off, which is your like photon energy. What else for resistance? What else? Ohmic are materials that have a constant resistance. Non-ohmic materials are ones that vary in resistance very easily. So a material that changes its resistance with a small amount of applied heat would be considered non-ohmic.
So you need resistance by circuit
Absolutely. If you remove the resistance in the circuit, you have nothing that can bear the load from the battery. The battery provides this energy that has to be used up by something. If not, those charge carriers get back to the battery and they want to get like re-energized, but they already have energy. So you need to have something that's dissipating or using the energy in the circuit. Without that, we call that a short circuit. By the way, in the other class, I drew this diagram because I don't think I ever drew it before. This is what a circuit breaker is. It's just a switch. That's all a circuit breaker is a switch. So a circuit breaker is open if there's too much current. But if the resistor, it breaks the circuit. If the resistor is in place properly like it is here, the circuit breaker remains closed. Well, suddenly there's a shorting in the wire and this path is created. Well, electrons want to follow the path of least resistance. So take a look, ready? Positive flow out of the positive terminal. It will take this path, it will bypass the battery, the resistor, and it will get to the circuit breaker. And the circuit breaker is going to say, oh my gosh, there's so much current coming through here. Why is there so much current? Because there's no resistor suddenly, there's a short. And the circuit breaker will then open up. Okay, as a result, opening the circuit. I can't erase this. Okay, but the circuit breaker detects too much current, it opens up, it trips the circuit, which shuts off your appliance, it shuts off the power being supplied to the appliance. You are closing the circuit. You're closing the switch. Because if that switch is open, the electricity can't flow, right? It's got to be closed. The loop has to be closed for electricity to flow. So my mom always says, apre la luce, open the light. In Italian, it's her saying. She says a lot of things in Italian, but you're not opening the light, right? You're closing the circuit. Is that clear? Yeah, turn on the light means really close the circuit.
Okay. I'll ask you to get some spicy meatballs.
No. So, power, write these down. Take a look at these three formulas for power. Each of them are useful. Depending on the scenario I give you tomorrow, depending on the scenario of what you're looking for. How do you know which one to use? You list your givens and list what you're looking for. If I give you power and I give you voltage and I say find the resistance, you automatically go to the third formula. You got power, you got voltage, you're finding the resistance. You pick that formula. Now, following up with these problems, we also need to use this formula. Because we need to remember that when we want to calculate the cost of energy, we need to know how much energy is being used. If I tell you how much power you're drawing by that bulb, and I tell you how much time it takes, you have to do power times time to give you the amount of energy. And that amount of energy should be in kilowatt hours. So your power, when you're using an electric bill, when you're doing a problem like that where I'm asking you to calculate the cost, your power unit should be kilowatts, your time unit should be hours. Again, I did a very lengthy math example of this. That's the other example in the video that you should look at. Okay, of all 19.3 with power and with energy involved with cost. Cost equals energy times rate. I don't think it's on the formula sheets. I think it's on yours, but I don't think it's on the one I laminated. So I'll put it on the board. Okay? Remind me though tomorrow, if it's not on the laminated ones, to put cost equals energy times rate on the board. But you should kind of know that by now. Okay? Yeah, all three of these are on there, and power equals work over time is on there, which is the same thing as energy over time. But it's earlier in the year. This is on there much earlier in the year with mechanical power. It's written as work over time, but work is energy. Okay, this is on earlier in the year as this. Work over time. But work is the same thing as energy over time. Bless you. 20-1, you should know the basic elements of a circuit. You should be able to draw a circuit if I give you a scenario. For example, if I say a battery is connected to a toaster, which is connected next to a light bulb, which is connected to a switch, draw that circuit. I said a battery connected to a toaster. Here's the battery. Connected to a toaster. Here's the toaster. Which is connected to a light bulb. Here's the light bulb. Which is then connected to a switch. I didn't say if it was open or closed, so just draw a switch. And then maybe I'll say there's two batteries actually next to each other. So I would draw another battery there. Now that's two batteries. Remembering that this is the positive terminal here. So the flow would go out of the positive terminal, through the switch, through the bulb, through the toaster, back to this end, if it was direct current, right? If I say draw an open circuit, what should you do to the switch? Just open the circuit, literally. Okay, the switch would look like this instead, and you would erase this part here in the middle. This part would not be there. And that would be empty space right there, and the switch would be open. But for 20-1, that's really the only ideas that I went through. We talked about these different elements and the basics of a circuit, but that also ties into chapter 19. Okay, questions? I saw a hand go up.
No, I was
Tom?
you are.
You sure? I saw another hand though too. It wasn't just Tom. Somebody else had a hand up. Okay, it's about 12:12. The bell's going to ring in a minute. So tonight, you should make sure to watch the math videos, please. Okay, please watch those math. Just go to videos from class. You'll see test review, and then test 10 math review. Or something like that. I forget what I need, but it says math.